Okay, um, so we've talked about the periodic table, and we've talked about the fact that there's a very special group of elements on the periodic table that we call the noble gases. They're this column right here. And the thing that makes the noble gases very special is that they are unreactive. Okay, so the noble gases, we can give them several descriptors. They used to be called inert, which means they don't react with anything, but over the past 40 years, people have been able, under very extreme conditions, to get substances like xenon and krypton to react and form a small number of compounds. So the name inert was changed to noble referring to nobility, kind of untouchable. It also means that they're very stable. Something about their atomic structure makes them such that they have no need or no driving force to combine with other atoms. Again, the driving force for chemical reactions and for the formation of compounds is seeking a more stable arrangement. In most cases, atoms combined with other atoms is more stable than individual elements, but the noble gases are kind of an exception. So they provide a benchmark of stability. And as we're going to see, compound formation can be explained by this model that atoms are attempting to achieve noble gas electron configurations either by transferring electrons or sharing electrons. Okay, so getting ahead of the story a little bit. When atoms bump into each other, first of all, chemistry happens when atoms collide. Atoms must collide. Okay, and if you think about our nuclear model of the atom, when atoms collide, the first region of collision, obviously, is the outermost part of the atom. And guess what's found in the outermost part of the atom? The valence electrons. So hence, the valence electrons are the key to talking about chemical reactions. Remember that from the periodic table, we can tell, at least for what we call the main group elements, the number of valence electrons. One valence electron here in this column, two here. We skip over the transition elements for right now. 3, 4, 5, 6, 7, and 8 valence electrons for the noble gases, except for helium, which, because it's in the first row, only has 2 valence electrons. Okay, so only 3 possibilities when atoms collide. Nothing happens. So imagine that a neon and a helium atom bump into each other. Nothing happens. When nothing happens, that's telling us that these substances that are colliding are already as stable as they can get, and there's no getting more stable. The second thing that can happen is that they transfer electrons to become more stable, and transferring electrons is the basis of a large category of compound formation that we call ionic bonding. And that's what we're going to talk about a little bit in this little talk. Okay. And then the third possibility is that they share electrons. They cooperate. Atoms cooperate, share electrons, and that sharing results in the formation of molecules, and we call that covalent bonding. So, believe it or not, those 3 possibilities explain just about all of what happens when chemical reactions happen. Okay, seems almost a little bit too simple. We're going to focus on this second possibility today. And again, we come up here and we look at the noble gases as being our benchmark of stability. And our model is that the rest of the atoms in the periodic table are looking to try to mimic the noble gases. Mimic is a fancy way of saying look like. Mimic the noble gases. And the thing that other atoms are trying to mimic is mimic the number of valence electrons. Okay, and I'm going to use this E with a negative sign on it to shorthand for electrons. Okay, so mimicking the number of valence electrons. So let's talk about a little tool. Let's take an example. Let's talk about sodium. Sodium, Na on your periodic table. Again, knowing the names and symbols of the more common elements is really useful in your study of chemistry. That's why your chemistry teacher has asked you to memorize some of the more popular elements. So sodium, Na, has one valence electron. And we've got a nice little tool that we use to show that one valence electron. We put a little dot next to it. That little dot is meant to represent the one valence electron. And that little dot method was developed by a guy named G.N. Lewis back in the early part of the 1900s. And they have become to be known fondly in chemistry as Lewis dot structures. Okay, they allow us to keep track of valence electrons. I'm going to put chlorine in a different color just for fun. Okay, chlorine is sitting over here at the other end of the periodic table, and chlorine is up here in column number 17. Everybody in column number 17 has 7 valence electrons, so we're going to use the dot structure of chlorine and show it with 7 valence electrons. Okay, now we start taking a little peek. Okay, we're looking at the noble gases. Okay, and we're saying to ourselves, what is the shortest route for an atom to get to the same configuration, the same number of valence electrons as a noble gas? Well, here's the situation. If you're on this side of the periodic table, like sodium, sodium is sitting here with 11 electrons. Okay, neon is sitting over here with the perfect number of 10. If sodium can somehow figure out how to lose 1 electron, it becomes the same number of electrons as neon. So that sounds like a pretty good deal. On the other hand, chlorine is sitting over here right next door to argon. Chlorine is sort of in the opposite situation. If chlorine can gain 1 electron, it suddenly becomes an ion with the same number of electrons as argon. So this looks like a pretty good deal. So when a sodium atom and a chlorine atom bump into each other, what they do is the sodium, okay, donates or transfers its electron to the chlorine. Okay, and in the process of that transfer, the sodium loses an electron, transfer electron. The sodium loses an electron, the chlorine gains an electron. They both started out neutral. If it loses an electron, okay, sodium now becomes a sodium with a +1 charge. It now has 10 electrons. It still has 11 protons, so it has a +1 charge. Chlorine now suddenly has done what? Chlorine, let me go back to my color scheme going here. Chlorine has gained an electron, so it has the 7 valence electrons that it started with, plus it now has that extra electron, and we'll show that in green, that the sodium transferred to it, so it has gained electrons, so it now has a negative charge. Okay, the chlorine now has 18 electrons. The chloride ion has 18 electrons. It still has its original 17 protons. It has a -1 charge. Okay. Wow. Both of these electrons are isoelectronic with noble gases. 10 electrons make sodium ion isoelectronic. Again, that word means same number of electrons. Anytime you see the prefix iso, that means the same. Isoelectronic with neon. Here's the simple idea. Neon is stable, therefore a sodium ion is stable. Okay? On the other hand, chlorine has 18 electrons. It is what? Look at the periodic table. It's isoelectronic with, look at the periodic table, by gaining that 1 electron, chlorine has become isoelectronic with argon. Argon has 18 electrons. A chloride ion has 18 electrons. So a chloride ion is isoelectronic with argon. They both have the same number of electrons. These are stable ions. Nature loves stability. Therefore, the transfer of these electrons is a good deal for both ions. The atoms become ions. The reactive atoms become stable ions. Now, what else happens? Notice that we have a +1 ion and we have a -1 ion. And what do opposites do? Opposites attract each other. So now what happens is that there's a very strong attractive force called the electrostatic force, one of the strongest forces in nature. And that electrostatic force causes what to happen? It causes that sodium ion and that chloride ion to be strongly attracted to each other, and hence we get the ionic bond. Okay? Two ions, two stable ions, strongly attracted to each other, and the formula is the simplest ratio that makes neutrality. So the formula is NaCl, the +1 sodium and the -1 chloride, exactly but cancel each other out. So the net charge on the compound is 0, and we call the compound sodium. We always name the metal element first, sodium, and then we start to spell out chlorine, but we add a special ending on there, IDE, to let us know that we have now formed a different substance. We have formed a compound. So the compound's name is sodium chloride, and the compound's formula is sodium chloride, NaCl, and the whole idea here is stability by transferring electrons. All right. We'll pick up there next time.